A star 20 times bigger than our Sun collapses in less than 1 second. The entire core, heavier than the Sun itself, crushes down to a ball 12 miles across. 1 teaspoon of what remains weighs 2 trillion pounds. We are going inside a neutron star, where iron hardens into something stronger than diamond, where matter warps into pasta shapes, and where the inner core holds secrets that physicists still cannot solve. If you enjoy the journey, subscribe and stay with us. Let's begin. Picture the biggest thing you have ever seen: a skyscraper, a mountain, an ocean. Now picture something that makes all of those look like dust. A star 20 times heavier than our Sun has been burning for 10 million years. Every second of every day, it crushes hydrogen into helium deep in its core. And that constant burning pushes outward, fighting gravity. The two forces balance perfectly, and the star holds its shape. For 10 million years, that balance never breaks. Then, it runs out of fuel. The moment the burning stops, gravity wins. There is no slow decline here. No gradual collapse. The entire core, a ball of matter heavier than our whole Sun, falls inward in less than 1 second. 1 second. Your heart beats slower than that. To understand what 1 second means here, think about dropping a bowling ball from the top of the Empire State Building. It takes about 9 seconds to hit the ground. The core of this dying star collapses faster than that. The whole thing, billions of miles of stellar material, falls inward before you finish blinking. The speed of that collapse is almost impossible to picture. Imagine the entire city of Los Angeles compressed into a space smaller than a football field. In the time it takes you to snap your fingers, the pressure during that collapse reaches levels that do not exist anywhere else in the universe except inside black holes. And that pressure does something extraordinary. Electrons and protons, the tiny particles that make up every atom in your body, get crushed together so hard they merge. They stop being electrons and protons. They become neutrons, billions upon billions of particles fusing into a single new type of object in under a second. The outer layers of the star do not survive this event quietly. The shock wave from the collapsing core blasts outward at millions of miles per hour. It tears through the rest of the star, ripping it apart in one of the most violent explosions the universe ever produces. A supernova. For a few weeks, that explosion shines brighter than an entire galaxy of 400 billion stars. But something survives the explosion. At the center of all that destruction, the crushed core remains. It does not explode. It holds together under its own gravity, squeezed into a perfect sphere about 12 miles across. That is roughly the distance from one end of a large city to the other, 12 miles wide. And inside that 12-mile ball sits more mass than our entire Sun. Scientists call it a neutron star. Astronomers have found about 3,000 of them scattered across our galaxy. And every single one started the same way. A massive star burned for millions of years, then died in under 1 second, leaving behind this tiny impossible object. The numbers alone are hard to process. The Sun has a diameter of about 860,000 miles. A neutron star has a diameter of 12 miles. You could line up 70,000 neutron stars side by side and still not match the width of our Sun. And yet the neutron star is heavier. The death lasted 1 second. The object it created will last longer than the current age of the universe. Something that violent and that fast leaves behind a world stranger than anything we imagined. The surface alone will change how you think about solid ground. And what lives just below that surface is where things get deeply, truly weird. In the summer of 1967, a young graduate student named Jocelyn Bell sat in a field in England, surrounded by 2,000 wooden poles and nearly 200 miles of wire she had spent months helping to build. The device was a radio telescope, a machine designed to listen to the sky. Bell's job was to read the data it produced, long rolls of paper covered in squiggly lines that represented radio signals arriving from space. Day after day, she read through yards of printouts, looking for anything unusual. Then she found something, a signal arriving with perfect regularity every 1.3373 seconds. Perfectly spaced, perfectly timed, like a clock. Like something built to send a signal, the pulse repeated so precisely that Bell and her supervisor initially ruled out natural causes. Stars did not behave this way. Planets did not behave this way. Nothing in nature was supposed to pulse that cleanly. They labeled it LGM-1, Little Green Men 1. That label was partly a joke, but only partly. The team genuinely could not explain the signal using any known natural phenomenon. For weeks, the source remained a mystery. Then a second pulsing signal appeared from a completely different part of the sky. Then a third. Aliens building 4 separate transmitters across the galaxy seemed unlikely. Something natural was causing this. The answer, when it came, was stranger than the alien theory. A neutron star spinning hundreds of times per second, blasting beams of radio energy from its magnetic poles, sweeping those beams across the galaxy like a lighthouse beam sweeps across the ocean. Every time one of those beams swept past Earth, radio telescopes detected a pulse. The star itself was the clock. Bell had discovered the first known pulsar. She was 24 years old. The discovery would later be recognized as one of the most important in the history of astronomy. The Nobel Prize for the work went to her supervisor. Bell did not receive it. To this day, many scientists consider that one of the great injustices in the history of scientific awards, what made the signal so unnervingly precise, is connected to something fundamental about neutron stars. These objects spin. They spin incredibly fast. A normal star like our Sun rotates once every 25 days. A neutron star can complete 400 full rotations in a single second. That is faster than the blades inside a kitchen blender. The reason comes down to physics. When a large star collapses into a tiny neutron star, it conserves its spinning motion. A spinning skater pulls their arms inward and speeds up. A collapsing star does the same thing on a scale that defies imagination. All that rotational energy compresses into a ball 12 miles wide, and the spin rate explodes. Pulsars are neutron stars aimed in a direction where their beams happen to sweep past Earth. Scientists use them as some of the most precise natural clocks in existence. The timing is so perfect that astronomers use pulsars to detect disturbances in space itself. A spinning ball of neutron matter, 12 miles wide, sending signals across thousands of light years with more accuracy than most human-built clocks. And the spin is just the beginning. The real force driving those beams, the engine behind the pulsar, comes from something almost incomprehensible. A magnetic field so powerful it rewrites the rules of space around it. Hold a basketball in your hand, feel the weight of it. Now imagine that basketball somehow contained the mass of 2 million Earths. That is what a neutron star is. The numbers sound made up. Scientists themselves spent decades arguing over whether objects like this could even exist. The math seemed to break. How could something 12 miles wide weigh twice as much as our entire Sun? The Sun is 860,000 miles across. A neutron star is 12 miles across. And the neutron star is heavier. To understand how this is possible, you have to understand what normal matter actually is. Your hand, the chair you might be sitting on, the ground beneath you, all of it is almost entirely empty space. An atom is mostly nothing. The nucleus at the center of an atom is tiny, and the electrons orbiting it are even tinier. The space between them is enormous by comparison. If a single atom were blown up to the size of a football stadium, the nucleus would be a marble sitting on the 50-yard line. All that empty space in matter is what makes things feel solid. But gravity does not care about empty space. Given enough force, gravity compresses matter by eliminating the gaps. A neutron star does exactly that. The collapse of the dying star generates enough gravity to crush atoms completely. Electrons and protons merge, and the empty space vanishes. What remains is packed so tightly that the particles are nearly touching. The density you get from that compression is beyond anything we have words for. 1 teaspoon of neutron star material would weigh about 2 trillion pounds on Earth. 2 trillion. A fully loaded aircraft carrier weighs around 200 million pounds. You would need 10,000 aircraft carriers to match the weight of a single teaspoon from this object. Another way to picture it: if you took Earth and compressed it to neutron star density, the entire planet would fit inside a marble. Every mountain, every ocean, every city, every human being, compressed into a marble-sized ball. The gravity at the surface of a neutron star is 200 billion times stronger than Earth's gravity. Standing on the surface would crush you with a force so immense that the word crushing does not come close to describing it. Every atom in your body would be torn apart before you could register the sensation. And the mass keeps doing something incredible. It warps the space around the star. General relativity, the theory Einstein developed to describe how mass bends space, gets pushed to its absolute limit near a neutron star. Space curves so sharply around these objects that light itself cannot travel in a straight line nearby. The star also pulls on time. Clocks run measurably slower near a neutron star than they do far away. If you could somehow hover safely close to one, time around you would slow while the rest of the universe kept moving at full speed. All of this from an object a city could cover. The mass creates the gravity shapes the space, and the space bends everything that comes near it. But beneath that extreme gravity, the surface of the star has its own story, a rigid, crystalline shell that is harder than anything we have ever made. Stand on the surface of a neutron star, and you are standing on iron, solid, crystalline iron, locked into a rigid lattice that stretches across the entire surface. The crust of a neutron star is roughly 1.2 miles thick, and it is made almost entirely of iron nuclei packed so tightly together that the structure makes diamond look fragile. Diamond is the hardest natural material on Earth. It scores a 10 out of 10 on the hardness scale we use to rank minerals. The crust of a neutron star scores billions of times higher. Scientists estimate it is 10 billion times stronger than the best steel ever produced in any factory on Earth. The material is so rigid that the vibrations from a starquake, an earthquake equivalent on a neutron star, travel through the crust faster than the speed of sound on Earth. How does iron end up on the surface of the densest object in the universe? When the star first forms, the outermost layers cool rapidly compared to the scorching interior. The iron nuclei that exist at this depth do not have enough energy to keep moving freely. Gravity locks them into place, one by one, until they form a perfect crystal grid. Each nucleus sits in its spot, held by electromagnetic forces, unable to move. The grid extends across the entire surface, billions of square miles of crystalline iron. The pressure holding this crust together is gravity, the same force that crushed the star's core, now acting as a kind of glue. Remove the gravity, and the crust would fly apart instantly. With the gravity, it holds tighter than anything in human experience. Underneath the lattice structure, free electrons move through the spaces between the iron nuclei, carrying heat and electricity the way electrons do inside a metal wire. This makes the crust electrically conductive, similar to how copper conducts electricity, but many orders of magnitude more efficient. The surface temperature of this iron crust reaches 1 million degrees. 1 million degrees Fahrenheit. That is roughly the same temperature as the outer atmosphere of our Sun, the corona, which itself is one of the great mysteries in solar science. On a neutron star, that temperature is the cool outer skin, and yet the crust is remarkably smooth. The same gravity that makes the surface so lethal also flattens everything. Any bump, any rise in the surface, gets pulled down almost instantly. The tallest features on the crust of a neutron star stand no higher than a few millimeters. On Earth, that would be a pebble. On a neutron star, that pebble-sized rise represents the most extreme mountain the gravity will allow. The crust holds together until something disturbs it. Occasionally, the stress builds, and the crust cracks. These events are called starquakes. They release enormous bursts of energy, sometimes visible across the galaxy, in what astronomers call magnetar flares. One magnetar flare detected in 2004 briefly outshone every other object in the Milky Way. A 1-inch tall mountain, made of iron harder than diamond, sitting on a surface burning at 1 million degrees. And this is just the outer skin. Below the crust, the rules change completely. Drop a single grain of sand from 1 inch above the surface of a neutron star. By the time it hits, it is traveling at roughly half the speed of light. The impact releases energy comparable to a nuclear weapon. From 1 inch, from a single grain of sand, that is what gravity does on a neutron star. And that same gravity is the reason the surface is flatter than anything humans have ever built. On Earth, mountains form because the rock underneath them is strong enough to support the weight above. The Himalayas rise almost 6 miles because the continental crust is thick and rigid enough to hold that mass in place. Gravity pulls them down, but the rock pushes back. The balance between those two forces lets mountains exist. On a neutron star, gravity wins that contest by a factor that has no comparison in everyday life. Surface gravity there pulls 200 billion times harder than Earth's gravity. No known solid material can resist that force. The iron crust, despite being 10 billion times stronger than steel, still cannot push back hard enough to support any meaningful height. Scientists calculate that the maximum height of any feature on the surface is somewhere between a few millimeters and about half an inch. Some estimates put the ceiling even lower. The entire surface of a neutron star, stretched across an area roughly the size of a major city, is smoother than a billiard ball when scaled to size. To put that another way, if you shrunk a neutron star down to the size of a bowling ball, the surface would be smoother than the smoothest bowling ball ever polished. The smoothness has consequences for how the star behaves. Because the surface is nearly perfect, rapidly spinning neutron stars lose very little energy to wobble or vibration. They spin like ideal tops. This is part of why pulsars keep such precise time. There is almost no imperfection in the rotating object to disrupt the rhythm. When astronomers detect a starquake, a sudden cracking of the crust, they can actually measure the mountain that formed. In 2016, a team studying a pulsar detected a glitch in the spin rate, a tiny speed-up caused by a crack in the crust releasing tension. That crack created a surface feature estimated at less than half an inch tall. The energy released in the process would have vaporized the surface of Earth many times over. Half an inch. Enough energy to destroy a planet. That ratio tells you everything about the scale of forces operating inside this object. The tiniest physical change on the surface of a neutron star produces consequences that dwarf anything in human experience. The gravity keeps the surface flat, keeps the spin precise, and compresses the crust into its extraordinary hardness. But it also does something more personal. If a person could somehow reach the surface, gravity would not just crush them, it would stretch them first, pulling harder on their feet than their head, tearing the body apart before it even landed. The surface alone is lethal in a dozen different ways. But going deeper, just a few hundred feet below the crust, the environment becomes something even harder to describe. Matter itself starts to fall apart. Take a teaspoon, the kind you use to stir coffee, fill it with neutron star material, set it on a scale. The scale would read 2 trillion pounds. A number that large has no real meaning until you stack it against something familiar. A blue whale is the heaviest animal on Earth. It weighs about 400,000 pounds. To match the weight of that teaspoon, you would need 5 billion blue whales. Every blue whale that has ever lived, every blue whale alive right now, and several billion more, all piled on a scale, still might not reach the weight of a single teaspoon from the surface of a neutron star. A fully loaded cargo ship carries about 400 million pounds of freight. You would need 5,000 of those ships to match the teaspoon. Line those ships end to end, and the line stretches from New York to Los Angeles and back 4 times. The reason for this impossible density comes back to what happened during the collapse. Normal matter is, as discussed before, almost entirely empty space. When the star died and the core crushed inward, all that empty space inside atoms got eliminated. Electrons merged with protons, the particles that survived. The neutrons packed together with almost no space between them. The result is a material where the distance between individual particles is roughly the same as the size of the particles themselves. On Earth, atoms in a solid are still separated by enormous gaps relative to the nucleus. In a neutron star, those gaps are gone. The density of the material varies as you go deeper into the star. The outer crust is the least dense layer, and even that is already denser than any material ever created in a laboratory. As you descend, the density climbs rapidly. Scientists measure the density of atomic nuclei, the tiny center of an atom, as a reference point. It is the densest naturally occurring thing in everyday matter. The outer layers of a neutron star reach similar densities. The inner core surpasses it by a factor of 5 to 10. 5 to 10 times denser than the center of an atom. There is no material in ordinary experience that comes anywhere close. Osmium is the densest metal on Earth. Neutron star material is roughly 1 trillion times denser than osmium. The weight of that teaspoon would also change the planet if it arrived here. 2 trillion pounds concentrated in a tiny space would punch straight through the Earth, pulled by gravity toward the center. It would pass through the mantle, through the outer core, and settle at the center of the planet, where its gravity would disrupt the Earth's interior in ways that would be catastrophic. The density does not just affect weight, it changes time, bends light, and alters the behavior of every physical force near it. The gravity produced by 2 trillion pounds in a teaspoon-sized volume curves space around it measurably. The outer surface already does all of this, and the deeper you go into the star, the less the matter inside resembles anything in a chemistry textbook. Something fundamental begins to break down just a short distance below the surface. 1 million degrees stand far enough away from a neutron star that gravity cannot reach you, and the light coming from its surface would still carry more energy than the surface of our Sun. The neutron star's surface temperature hits 1 million degrees Fahrenheit, roughly the same temperature as the Sun's outer corona, that shimmering halo visible only during a solar eclipse. On our Sun, that million-degree temperature is a mystery. The surface of the Sun itself is only about 10,000 degrees. The outer atmosphere somehow jumps to 1 million, and scientists have spent decades debating why. On a neutron star, 1 million degrees is just the skin. Immediately after a neutron star forms, the interior temperatures are far higher, reaching around 1 trillion degrees in the first few seconds. Slowly, over hundreds of thousands of years, the star radiates that energy away. The surface cools from the outside while the interior stays hot much longer. After about 1 million years, the surface temperature settles around 1 million degrees and stays there for a long time. That heat radiates outward as X-rays. Neutron stars glow primarily in X-rays, which are invisible to the human eye but detectable to space telescopes. Some of the most important neutron star discoveries came from X-ray telescopes orbiting Earth, scanning the sky for these intense, invisible signals. The temperature also shapes what happens on the surface in ways that are hard to picture. The iron crust, despite being harder than any earthly material, glows brilliantly. The photons streaming off the surface are so energetic that ordinary glass would be no protection at all. Even from a safe distance, the radiation environment near a neutron star would be lethal to any living thing. The temperature gradient across the star is extreme. 1 million degrees on the surface, somewhere around 100 million degrees in the deeper crust. and climbing steeply as you descend toward the core, where the temperature reaches levels tied to the density of the matter itself. Interestingly, neutron stars cool unevenly. Different spots on the surface radiate at slightly different temperatures, and astronomers can map these temperature differences across the surface. The patterns reveal information about what is happening inside the star, what layers exist, and how they interact. Younger neutron stars are significantly hotter and brighter. Older ones have dimmed over millions of years, though they never fully go cold. They remain hot enough to glow in X-rays for billions of years. The relationship between the surface temperature and the interior is one of the tools scientists use to understand what is happening deep inside. The speed at which a neutron star cools tells researchers about the type of matter in the core. A star that cools too quickly suggests something unusual is going on at the center, releasing extra energy through channels that normal neutron matter would not use. A glowing iron shell at 1 million degrees, radiating X-rays into the dark. And yet, despite all that heat, nothing escapes the neutron star easily. Escaping the surface requires hitting a speed that almost nothing in the universe can reach. Throw a ball into the air on Earth. It slows down, stops, and comes back. You know why. Gravity pulls it back. To escape Earth's gravity permanently, you need to throw that ball at 7 miles per second. That is faster than any bullet ever made. Rockets do it not by hitting that speed instantly, but by burning fuel continuously to keep pushing against gravity all the way up. On a neutron star, the number that defines escape is in a completely different category. To leave the surface of a neutron star and never come back, you need to be moving at roughly 62,000 miles per second. That is about 1/3 the speed of light. The speed of light itself is 186,000 miles per second, the fastest anything in the universe can travel. You would need to be moving at 1/3 of that absolute maximum speed just to walk away from the surface. For comparison, the fastest spacecraft ever launched by humans, the Parker Solar Probe, reached a top speed of about 430 miles per second, an incredible achievement. The escape velocity of a neutron star is 140 times faster than that. What does this mean practically? It means almost nothing that falls onto a neutron star ever leaves. Particles, gas, dust, radiation, everything that drifts close enough gets pulled in with no path back. Light itself, the fastest thing in existence, leaves the surface with great difficulty. The photons that manage to escape do so at a cost. They lose energy fighting the gravity. This energy loss is visible and measurable. Astronomers call it gravitational redshift. A photon leaves the surface carrying a certain amount of energy, and by the time it reaches a distant telescope, it has lost a measurable fraction of that energy to the gravitational pull it had to fight. Measuring that redshift tells scientists the ratio of the star's mass to its radius, a crucial piece of data for understanding what kind of matter lives inside. The escape velocity also tells us something profound about the star's place in the universe between normal stars and black holes. A black hole has an escape velocity equal to the speed of light, or greater. Nothing escapes. A neutron star sits just below that threshold. Its escape velocity is 1/3 the speed of light, close enough to the black hole limit that it occupies a strange middle zone. Add enough mass to a neutron star, and the escape velocity climbs until light cannot leave. The neutron star collapses into a black hole. There is a maximum mass a neutron star can hold before that happens. Scientists call it the Tolman-Oppenheimer-Volkoff limit. Estimates put it somewhere between 2 and 3 solar masses. Go above that, and no known force can stop the collapse into a black hole. Neutron stars exist in a narrow band between impossible density and total gravitational collapse. They survive by the thinnest of margins. Below the surface, something helps maintain the structure, a boundary layer where matter itself starts losing its identity, where atomic nuclei crack open and shed their contents into the surrounding space. A line that once crossed going downward changes everything. 0.6 of a mile below the surface, something breaks. The iron crust above is already extraordinary. Dense, rigid, burning hot. But the iron nuclei in the crust still behave like nuclei. They hold together. The protons and neutrons inside them stay bound. Atoms, in some form, still exist down there. At 0.6 of a mile deep, they stop existing. This boundary has a name. Scientists call it the neutron drip line. It marks the depth where the pressure becomes so extreme that atomic nuclei can no longer hold themselves together. The neutrons inside the nuclei, which were bound tightly by the nuclear force, start leaking out. They drip free, flooding the space between the remaining nuclei with a sea of loose neutrons floating around without any atom to belong to. The nuclear force, the strongest force in nature, is the glue that holds protons and neutrons together inside a nucleus. It is incredibly powerful but extremely short range. It only works across distances smaller than a single proton. Inside a healthy nucleus, that force operates perfectly, binding everything together. But below the neutron drip line, the external pressure is so great that it overcomes even the nuclear force at the edges of the nucleus. Neutrons get squeezed out. Picture a water balloon being squeezed. At some pressure, the water starts leaking through the rubber. That is what happens to the nucleus here. The nuclear force is the rubber, and the immense gravity of the neutron star is the hand squeezing. The neutrons that drip free do not decay. On Earth, a neutron outside a nucleus lasts about 15 minutes before breaking apart into a proton, an electron, and a tiny particle called an antineutrino. That decay happens because, in normal conditions, it is energetically favorable for the neutron to break down. Inside the neutron drip zone of this star, the extreme pressure and density make that decay energetically impossible. The neutrons are stable because the environment forbids them from changing. The drip zone creates a new kind of material, a mix of nuclei, free neutrons, and electrons, all coexisting under crushing pressure. The free neutrons fill the space between nuclei the way water fills the gaps between rocks in a riverbed. The deeper you go, the more neutrons drip free, and the fewer intact nuclei remain. This is the beginning of the transition from the crust to something stranger below. The neutron drip line is not just a boundary in space. It is a boundary in the nature of matter itself. Above it, atoms still make sense. Below it, atoms dissolve. Scientists study this region using mathematical models built from nuclear physics experiments on Earth. No laboratory can recreate the pressure of the drip line directly, so everything known about this layer comes from inference, from what the equations predict when you push the numbers to extremes. And just below this region, the matter does something even harder to explain. The competing forces of gravity and nuclear repulsion, pressing against each other at the edge of what physics can handle, shape matter into structures with names borrowed from the dinner table. A free neutron lives for 15 minutes. Set a neutron loose outside a nucleus here on Earth and start a timer. In about 15 minutes, it breaks apart. It transforms into a proton, shoots out an electron, and releases a tiny particle called an antineutrino. Scientists have measured this lifetime precisely. It is one of the most well-tested numbers in particle physics. Now go to the neutron drip zone, 0.6 of a mile below the surface of a neutron star. Free neutrons exist there in enormous numbers. They have dripped out of their nuclei and are floating loose, exactly the way they would be on Earth. By every rule of particle physics established in any laboratory, they should be decaying. 15 minutes, and gone. They do not decay. They stay intact, stable, floating in the drip zone without breaking down for as long as the star exists, which is billions of years longer than the universe has existed so far. The reason sits in a principle of quantum mechanics called the Pauli exclusion principle. This rule states that no two particles of the same type can occupy the same quantum state at the same time. Think of quantum states as seats in a theatre. Each seat can hold exactly one particle. When all the seats are full, no new particles can sit down. In the drip zone, the neutron density is so extreme that every available quantum state is already filled. The decay of a neutron produces a proton and an electron. For that decay to happen, the proton and electron need somewhere to go. They need an empty quantum state to land in. In the drip zone, there are no empty seats. Every possible state is taken. The decay cannot happen because the products of the decay have nowhere to go. Scientists call this quantum blocking. The density of the environment makes a normally unstable particle permanently stable by closing off every exit route. This is one of the places where quantum mechanics and extreme astrophysics collide in a way that produces genuinely new physics. The rules that apply to a single neutron in a vacuum do not apply to a neutron inside a neutron star. The stability of these free neutrons is essential to the star's existence. Without it, the star would dissolve from the inside. The free neutrons would decay, the products would pile up in ways that destabilize the structure, and the star would change dramatically in a short time. Instead, the quantum lock holds everything in place. The drip zone sits stable, sustained by a rule that says overcrowding prevents change. There is something almost poetic about it. The most extreme environment in the universe uses the same quantum rule that explains why atoms are solid, why electrons do not collapse into the nucleus, why matter holds its shape at all. The neutron star is the ultimate proof that quantum mechanics applies everywhere, even at scales and pressures that seem to mock the laboratory conditions where those rules were first discovered. The free neutrons hold their positions, and just below them, the forces acting on matter reach a new level of strangeness. The remaining nuclei do not just shed neutrons, they change their shape entirely, twisting into forms that physicists named after something completely unexpected. About 1.2 miles below the surface, the matter inside a neutron star stops looking like anything in a chemistry textbook. Here, two forces fight each other in a tug-of-war that reshapes the building blocks of matter. On one side, gravity pulls everything inward with crushing pressure. On the other side, nuclear repulsion, the force that pushes protons and neutrons apart when they get too close, pushes back. Both forces are operating at their absolute limits, and the matter caught between them gets deformed into bizarre shapes. Physicists who modeled this region in the 1980s gave those shapes the best possible names. The shapes look like pasta. Real, actual pasta. The first shapes that form as you descend into this region are called gnocchi, rounded blobs of nuclear matter, denser than anything above, floating in a sea of free neutrons. Further down, the blobs elongate under pressure into long, tangled cylinders. Those are called spaghetti. The cylinders are only a few femtometers wide, which is smaller than a single proton, but they stretch into long strands through the dense neutron sea. Descend a little further, and the spaghetti flattens. Long sheets of nuclear matter spread through the star, layered like pages in a book. Those are called lasagna. Each sheet is one of the densest flat structures that matter is physically capable of forming. The process continues in reverse as the geometry inverts. Tubes of empty space appear in solid nuclear matter, like spaghetti made of absence. Then spherical holes in solid material like Swiss cheese. Physicists call these antipasta phases because the structure flips. Instead of dense matter in a neutron sea, empty space sits in dense matter. The entire nuclear pasta layer is about 330 feet thick. 330 feet, roughly the height of a 30-story building. Inside that narrow band sits more mass than 3,000 Earths combined. The density in this layer is extraordinary. The gnocchi phase alone surpasses the density of an atomic nucleus. Everything below that is denser still. The lasagna sheets represent matter at densities that cannot be reproduced in any experiment on Earth. Scientists have never directly observed nuclear pasta. Everything known about it comes from computer simulations that run equations of nuclear physics at extreme conditions. What happens in these simulations is consistent across different research groups. The pasta shapes appear reliably, which gives physicists confidence they are real. But the exact properties of each phase, how the matter behaves mechanically and electrically, remain under active study. One finding stands out above everything else in this layer: something about its mechanical strength. When scientists ran calculations on how strong the lasagna phase is, how much force it takes to crack or deform the sheets, the answer was stunning. The nuclear pasta layer is the strongest material that physics allows to exist. Stronger than diamond, stronger than the iron crust above it, stronger than any material ever proposed in any context. And that extreme strength has a consequence nobody fully predicted. A 30-story building is about 330 feet tall. Now imagine a layer of matter that thin, containing more mass than 3,000 Earths, stacked together. 3,000 of the planet you are standing on right now, compressed into a band narrower than a city block is tall. The nuclear pasta layer sits about 1.2 miles below the surface of a neutron star. From above, the crust presses down with the weight of every layer stacked on top of it. From below, the pressure builds toward the core. The pasta layer exists in the middle of this crushing environment, and it holds a staggering amount of mass in a terrifyingly thin space. To picture the mass, Earth weighs about 13 billion trillion tons. 3,000 Earths would be a number so large that writing it out in standard notation would stretch across this page many times. All of that mass, packed into a layer 330 feet thick, the density of the nuclear pasta layer exceeds the density of a standard atomic nucleus, which is already the densest thing in ordinary matter. Inside the pasta layer, nuclei are so close together that the strong nuclear force, which normally only operates at extremely short range, starts connecting them. The boundaries between individual nuclei blur. Matter stops being made of separate atoms and starts behaving like one continuous tangled solid. This is where the mechanical strength of the material becomes truly striking. Scientists modeled the lasagna phase in detail, running simulations that calculate the forces involved in cracking the sheets. The result? It takes 10 billion times more force to break a piece of nuclear pasta than it takes to break a piece of steel. 10 billion times. Steel is already one of the hardest materials humans can produce. Nuclear pasta surpasses it by 10 billion. The only thing on Earth that comes close in terms of its resistance to deformation is diamond, and diamond is still nowhere near this league. The pasta layer is the hardest known material in the universe. Why does this matter? Because the hardness has physical consequences for the star. Starquakes on a neutron star happen when the crust or pasta layer cracks under stress. Those cracks release enormous energy. The harder the material, the more stress it can store before breaking, and the more energy it releases when it finally does. A crack in the nuclear pasta layer would release a burst of energy many times greater than the largest nuclear weapon ever built, all from a fracture in a region thinner than a city block is tall. Astronomers have detected bursts from neutron stars that are consistent with giant starquakes. Magnetars, a type of neutron star with especially powerful magnetic fields, sometimes emit flares that briefly outshine everything else in the galaxy. Some of those flares may originate from cracks propagating through the pasta layer. The pasta layer carries enormous mass, enormous strength, and enormous stored energy. And below it, the structure of matter changes again, in a way that should be impossible. The material transitions into something that flows without resistance, forever. Scientists spend careers searching for strength. They test carbon fiber, tungsten alloys, synthetic diamonds, and engineered ceramics. Military labs, aerospace companies, and universities all run experiments to find materials that resist breaking under the highest possible stress. The strongest materials humans have ever created are measured in units called gigapascals, a measure of how much pressure a material can withstand before it fails. Steel fails at about 1 to 2 gigapascals of shear stress. Diamond, the hardest natural mineral on Earth, survives up to about 100 gigapascals before it cracks. These numbers represent the limits of what chemistry and atomic structure can produce on this planet. Nuclear pasta survives at roughly 10 billion gigapascals. That number is so far beyond anything in human engineering that the comparison almost loses meaning. To crack a piece of nuclear pasta, you would need to apply a force that is 10 billion times greater than what it takes to shatter diamond. Scientists describe the material as effectively incompressible and nearly unbreakable under any force that does not involve a black hole or another neutron star. The strength comes from the geometry. In the lasagna phase, sheets of nuclear matter are held together not just by electromagnetic forces which hold normal solids together, but by the strong nuclear force itself. This is the most powerful fundamental force in nature, the force that holds quarks together inside protons and neutrons. In the pasta layer, it extends across the sheets, bonding matter at scales where normal chemistry does not apply. No laboratory on Earth can test this directly. The pressures needed to create nuclear pasta are far beyond any equipment humans have ever built. Everything known about its strength comes from computational physics, from solving the equations of quantum chromodynamics on powerful computers, and examining what the math predicts. Multiple independent research groups have run these simulations, and they consistently arrive at the same conclusion. The pasta phases are extraordinarily strong. Some groups have specifically highlighted the lasagna phase as the strongest, others point to the spaghetti phase, but all of them agree that the material surpasses any ordinary solid by many orders of magnitude. This has a practical consequence for neutron star astronomy. Scientists studying pulsar timing have noticed that some pulsars slow down very gradually over time, as expected from energy loss. But occasionally, a pulsar glitches, speeding up suddenly before settling back into its slow deceleration. Some of these glitches are thought to originate from mechanical events in the crust and pasta layer. The stronger the material, the longer it can store rotational stress before releasing it in a glitch. Understanding the strength of nuclear pasta helps astronomers build better models of pulsar behavior. The pasta layer acts like a shock absorber between the fluid core below and the rigid crust above, storing and releasing energy in ways that shape what we see from thousands of light years away. And just below this nearly unbreakable layer, something unexpected happens. The matter stops being solid at all. It becomes a liquid. And not just any liquid, but one that behaves in ways no liquid on Earth is capable of. Imagine stirring a bowl of water. The water swirls, slows, and stops. Friction between the water molecules and the bowl, and between layers of water moving at different speeds, gradually steals the energy and brings everything to rest. Now imagine a bowl of liquid that never stops. Stir it once, and it keeps spinning. Tomorrow, still spinning. A year from now, still spinning. 1,000 years from now, spinning at the exact same speed as the moment you stirred it. No energy lost. No friction. No slowing. That liquid exists inside a neutron star. Below the pasta layer, atomic structures completely dissolve. The outer core of the star consists of a dense ocean of free neutrons, with a smaller number of free protons mixed in. This ocean is not solid. The pressure keeps it from crystallizing. It flows like a liquid. And because of quantum effects at these extreme densities, the neutron ocean becomes a superfluid. Superfluidity is a real phenomenon, not a theory. Scientists created superfluids in laboratories using helium cooled to just above absolute zero. At that temperature, helium stops behaving like a normal liquid and enters a quantum state where all friction disappears. It climbs the walls of containers. It flows through microscopic holes that nothing else can pass through. It spins in vortices that persist forever without any energy input. The neutron star core does the same thing, but achieved through extreme density rather than extreme cold. The neutrons in the outer core pair up with each other in a quantum mechanical arrangement that eliminates friction entirely. The entire ocean of neutrons flows as a single coherent quantum system. The consequences for the star are significant. The superfluid core stores angular momentum, the spinning motion of the star, in a very specific way. Rather than spinning as one smooth mass, the superfluid contains billions of tiny tornadoes called vortices, each one a quantized unit of rotation. These vortices pin to the crystal lattice of the crust above. When the outer crust slows down slightly from energy losses over time, the vortices in the superfluid below are still spinning at the old faster rate. Periodically, the vortices suddenly release their stored rotation and kick the crust back to a faster spin. This is one of the leading explanations for the pulsar glitches that astronomers have observed for decades. A superfluid inside a star, spinning forever with no friction, communicating with the rigid crust above through billions of microscopic vortex lines. The protons in the same region do something equally strange. They form pairs under the extreme conditions and enter a state called superconductivity. A superconductor carries electrical current with zero resistance. On Earth, superconductors require cooling to near absolute zero. In the neutron star core, they exist at hundreds of millions of degrees, driven to that state by density alone. Superconducting protons generate and channel the star's magnetic field in ways that give neutron stars their extraordinary magnetic power. That power is responsible for the beams that make pulsars visible across the galaxy. A superfluid ocean below, a superconductor driving the magnetic field, and a crust spinning hundreds of times per second above, the system operates as one interconnected machine. And the machine's engine, the source of its most extreme power, runs on something that takes spin itself to a scale that seems impossible. Inside the outer core of a neutron star, a small fraction of the particles are protons. They are outnumbered massively by the surrounding neutrons, but they matter enormously. These protons form pairs under the intense pressure and density, and those pairs enter a quantum state that eliminates all electrical resistance. Every proton pair moves freely through the core without losing any energy to heat or collision. On Earth, electrical resistance is everywhere. Every wire, every circuit, every cable loses some energy as heat when electricity flows through it. Power lines stretch for hundreds of miles and lose a fraction of their energy along the way. Engineers spend enormous effort minimizing this loss, but eliminating it entirely under normal conditions is impossible. In a neutron star's outer core, the resistance is exactly zero. A current set in motion in the superconducting proton layer would flow without change, without loss, for longer than the universe has existed. The electrical current becomes permanent. This has a direct consequence for the magnetic field. The magnetic field of a neutron star is generated and maintained by these circulating currents of superconducting protons. On Earth, magnetic fields require continuous energy input to maintain. Turn off the power to an electromagnet, and the field disappears. In a neutron star, the superconducting currents that generate the magnetic field require no energy to sustain. They keep running indefinitely. The result is a magnetic field of staggering strength. The magnetic field of Earth measures about half a Gauss at the surface. The average neutron star has a magnetic field of around 1 trillion Gauss. That is 2 trillion times stronger than Earth's. Magnetars, a specific subtype of neutron star, reach fields of around 1 quadrillion Gauss, which is 1,000 times stronger still. To put that in perspective, a magnetic field of just 50,000 Gauss would be strong enough to damage the iron in human blood. A neutron star's field at 1 trillion Gauss would be felt at distances of hundreds of thousands of miles. It is strong enough to wipe all the data from a credit card at a distance greater than the Moon is from Earth. The magnetic field reshapes the space immediately around the star. It aligns the electrons and ions near the surface into tight bundles that can only move along magnetic field lines. It channels high-energy particles toward the magnetic poles. Those particles, accelerated to extreme speeds by the field, blast outward from the poles as powerful beams of radiation. The superconducting core produces the field produces the beams. The beams sweep across the galaxy at the rate of the star's rotation. When those beams sweep past Earth, we see a pulsar. This chain of events, from zero-resistance proton pairs deep in the core to radio signals received by telescopes on Earth, represents one of the most elegant mechanisms in astrophysics. The extreme physics inside the star connects directly to what we can observe from thousands of light-years away, and the rotation driving all of this reaches speeds that seem to mock the scale of the object producing them. A ball 12 miles wide, spinning hundreds of times per second, and the physics behind why it spins that fast changes something you thought you understood about motion. Hold your arms out wide and spin slowly on an office chair. Now pull your arms tight to your chest. Your spin gets faster. You did not add any energy. You just changed your shape. Physicists call this the conservation of angular momentum, and it governs everything from spinning skaters to dying stars. When a massive star collapses into a neutron star, the same principle operates at a scale that produces one of the most extreme spinning objects in the universe. The original star was enormous. Stars like the ones that form neutron stars are typically 10 to 20 miles across. No, 10 to 20 times the Sun's diameter, meaning they span roughly 8 million to 16 million miles. They rotate slowly, taking days or weeks to complete a single rotation. Then, the core collapses. In under a second, a region millions of miles wide compresses down to 12 miles. All the angular momentum that was spread across millions of miles of spinning stellar material gets packed into an object smaller than a city. The spin rate explodes. The physics demands it. Angular momentum must be conserved. The smaller the object, the faster it must spin to keep the same total angular momentum. A collapsing core does not choose to spin faster. Physics forces it to. The most extreme pulsars discovered rotate more than 700 times per second, 700 complete rotations every second. The equator of such an object moves at a speed of around 40% of the speed of light, just from the spinning. The star bulges slightly at the equator from centrifugal force, despite the crushing gravity working against it. These fastest spinning pulsars are called millisecond pulsars because the time between pulses is measured in milliseconds. Many of them were spun up to their extreme speeds not just from the original collapse, but from a second stage of acceleration. When a neutron star pulls material from a companion star in a binary system, that infalling material carries angular momentum of its own. It adds spin to the neutron star, the way water hitting a paddle wheel makes it turn faster. Over millions of years, this process can push a neutron star's rotation to hundreds of times per second. The fastest millisecond pulsars are among the most stable clocks in the universe. The timing of their pulses, once measured precisely, drifts by less than a microsecond per year. Scientists use them to detect gravitational waves by watching for tiny disturbances in their timing caused by ripples passing through space. The spin also ties directly into the heat coming off the star. Spinning so fast generates friction between the star and the magnetic field, anchored in its interior. This friction converts rotational energy into radiation, gradually slowing the star over millions of years. The spin-down rate is measurable, and from it, scientists can calculate the star's magnetic field strength. A star millions of miles wide, collapsing into a 12-mile ball in under a second, spinning 700 times per second as a result. That compressed spin drives a magnetic field strong enough to reshape space around it. And that magnetic field is where the next level of strangeness begins. Hold a refrigerator magnet to your skin. You feel nothing, but the magnet still has enough force to stick paper to the fridge from the other side. That tiny force, almost imperceptible, is what we consider a normal magnet. The magnetic field of Earth is stronger. It deflects charged particles streaming from the sun, protecting the planet from solar wind. Compasses align with it. It shields the atmosphere from being stripped away. A neutron star's magnetic field is 1 trillion times stronger than Earth's. 1 trillion, 12 zeros. To get a sense of that scale, if Earth's magnetic field were a flashlight, the neutron star's field would be brighter than the Sun by a wider margin than the Sun is brighter than a firefly. This field does things that no magnetic field in everyday experience can do. At the surface of a neutron star, the magnetic field is so intense that it warps the quantum vacuum itself. Empty space, which is never truly empty but filled with constantly appearing and disappearing quantum particles, gets reorganized by the field. Light traveling through it behaves differently depending on its orientation to the field. The polarization of light, the direction it vibrates as it moves, rotates as the light passes through the magnetized space near the star. This effect, called vacuum birefringence, was first measured around a neutron star in 2016, confirming a prediction of quantum electrodynamics made decades earlier. The field also restructures the atoms on the surface of the star. Normally, electrons orbit atomic nuclei in three-dimensional clouds. In a field of 1 trillion Gauss, electrons are forced into pencil-thin tracks along the field lines. Atoms become elongated, stretched along the field direction into cylindrical shapes nothing like their normal form. Chemistry in this environment is fundamentally different from chemistry anywhere else in the universe. The field does not stay neatly at the surface. It extends outward into space tens of thousands of miles in all directions. Any charged particle that drifts into this region gets captured and accelerated. The magnetic poles become particle accelerators, launching electrons and positrons to speeds approaching the speed of light. As these particles spiral along the field lines, they radiate energy. The result is the pulsar beam. Magnetars take all of this further. A magnetar is a neutron star with a magnetic field roughly 1,000 times stronger than an average pulsar. At those field strengths, the crust of the star is under constant mechanical stress from the magnetic pressure. The field pulls and twists the solid crust from the outside. Sometimes the crust snaps. The sudden release of magnetic energy produces what astronomers call a giant flare. In December of 2004, a magnetar located 50,000 light-years away released a giant flare. The burst lasted about 0.2 of a second. In that time, it released more energy than our Sun puts out in 250,000 years. The pulse was intense enough to partially ionize Earth's upper atmosphere from across the galaxy. A 0.2 of a second flash from 50,000 light-years away, reaching across the galaxy and touching our planet. The magnetic field generates the beam sweeps the galaxy, and somewhere deeper inside the star, something even more extreme waits. A region where the pressure exceeds the interior of any atom ever measured, and where the rules of physics themselves might be dissolving. The credit card in your wallet stores data on a magnetic strip. That strip contains a thin layer of magnetic particles, each one aligned to encode your account information. A strong enough magnet held close to the card can scramble those particles, wiping the data permanently. The field required to do that is a few hundred Gauss, the kind produced by a small industrial magnet, something you could hold in your hand. A neutron star's magnetic field reaches 1 trillion Gauss at the surface. That field does not stop at the surface. It radiates outward into space, weakening with distance but remaining powerful across enormous ranges. At a distance of about 300,000 miles from the star, the field has weakened considerably from its surface value. 300,000 miles is roughly 1.25 times the distance from Earth to the Moon. At that distance, the neutron star's field still measures in ranges that would completely erase every credit card, every hard drive, every magnetic storage device ever built by humans. The field at that distance would also affect biological tissue. Magnetic fields above about 45 Tesla, a unit of field strength, begin to influence chemical reactions inside living cells. They affect how molecules bond, how proteins fold, how nerve signals travel. The neutron star's field at hundreds of thousands of miles still exceeds that threshold by enormous margins. The practical meaning is simple. Long before any physical object got close enough to feel the heat or gravity of a neutron star, the magnetic field would have already altered its chemistry. In the immediate vicinity of the star, The field's effects go far beyond erasing data. Electrons in the field cannot move freely in 3 dimensions. The field lines act as rails, forcing every charged particle to spiral along them rather than travel in a straight path. Atoms near the surface lose their normal spherical shape entirely, squeezed into elongated forms aligned with the field direction. This reorganization of matter by magnetic force is not a side effect. It is a defining feature of the environment. The space within a few hundred miles of the surface is magnetically structured in a way that makes it unlike any other region in the observable universe. Scientists studying this region use X-ray telescopes to observe light coming from the surface and passing through the magnetized layer above it. The polarization patterns in that light carry information about the field structure. In 2022, a team analyzing data from a space telescope confirmed the magnetic field geometry around a neutron star by measuring the polarization of its X-ray emissions. The pattern matched predictions from quantum electrodynamics, a confirmation that required measuring effects playing out 50,000 light-years away. The field lines also guide energy transfer from the interior to the exterior. Heat moving upward through the crust does not spread evenly. It follows the magnetic field, flowing more easily along field lines than across them. This creates temperature patterns on the surface, hot spots and cool regions, that pulse with the star's rotation. Astronomers detect those temperature variations as brightness changes in the pulsar signal. The exact pattern tells researchers about the field geometry inside the crust, adding another layer of information to build a picture of the interior. A magnetic field vast enough to reach across hundreds of thousands of miles, strong enough to alter matter, redirect heat, and reshape space itself. And this field does one more thing. It creates the most recognizable signal in all of neutron star astronomy. Picture a lighthouse on a rocky coast. The light inside does not shine in all directions equally. It sits behind a rotating lens that focuses the beam and sweeps it in a circle. From far out at sea, a sailor does not see a constant glow. They see a flash, then darkness, then another flash, arriving at perfectly regular intervals. The lighthouse tells the sailor where they are. A pulsar works the same way, at a scale the sailor could never imagine. The neutron star's magnetic field channels high-energy particles toward 2 points on the star, the magnetic poles. Those particles, accelerating to near light speed, emit radiation as they spiral along the field lines. The radiation blasts outward from each pole as a tightly focused beam. The star rotates. The beam rotates with it. Anywhere in the galaxy where that beam sweeps past, a telescope detects a pulse, then silence, then another pulse arriving at exactly the same interval as the one before. The interval between pulses equals the rotation period of the star. For most pulsars, that interval falls between a few milliseconds and a few seconds. The fastest known pulsars pulse over 700 times every second, the slowest pulse about once every few seconds. Pulsar beams are among the most directional phenomena in nature. They are tight enough that from any given point in the galaxy, only a small fraction of all existing pulsars are visible. Their beams never swing past Earth. Scientists estimate that for every pulsar we can detect, there are many more that we cannot, simply because their beams point in other directions. The ones we do detect have given astronomers an extraordinary toolkit. The precise timing of pulsar pulses allows measurements that nothing else in astronomy can match. Pulsar timing arrays, networks of radio telescopes spread across multiple continents, monitor dozens of millisecond pulsars simultaneously. By carefully tracking tiny variations in pulse arrival times, these arrays can detect gravitational waves passing through the galaxy. A gravitational wave stretches and compresses space as it passes, and that distortion changes the apparent distance between Earth and the pulsar by a tiny measurable amount. In 2023, multiple pulsar timing array collaborations around the world announced the first strong evidence for a gravitational wave background. a low hum of gravitational waves filling the entire galaxy, most likely produced by pairs of supermassive black holes orbiting each other in the cores of distant galaxies. Pulsars made that discovery possible. Pulsars have also been used to test general relativity in extreme conditions. In binary systems where two neutron stars orbit each other, the timing of pulsar signals reveals the curvature of space between them. These systems have provided some of the most precise tests of Einstein's theory ever conducted. Every prediction from the theory has matched the pulsar data with extraordinary accuracy. One binary pulsar system discovered in 1974 provided the first indirect evidence that gravitational waves exist. The two stars were slowly spiraling inward at exactly the rate predicted by energy loss from gravitational wave emission. The scientists who discovered it received the Nobel Prize in Physics in 1993. A spinning ball 12 miles wide sends signals across thousands of light-years with enough precision to detect ripples in space-time. But the story of pulsars began with a moment of genuine confusion. And that confusion led to one of the most famous labels in the history of astronomy. Cambridge, England, August 1967. A new radio telescope had just come online, built from 2,000 wooden posts and nearly 200 miles of wire spread across 4.5 acres of countryside. Jocelyn Bell, a 24-year-old graduate student, was responsible for analyzing the data it produced. Every day, yards of paper chart recordings arrived, covered in wavy lines representing radio signals from space. Bell read through them by hand, marking anything unusual. In late August, she found something. A signal arriving with mechanical precision, every 1.337 seconds. A pulse, then another, perfectly spaced, perfectly regular. Bell marked it as scruff on her chart, an informal label for signals that did not fit normal categories. When she brought it to her supervisor, Anthony Hewish, they initially suspected the signal was interference from human-made equipment. A radio transmitter somewhere, perhaps. They checked. The signal moved with the stars, rising and setting on a sidereal schedule, the rhythm of objects fixed in space, not objects fixed on Earth. Whatever was producing it was out there. The precision of the pulses ruled out most known natural sources. Stars do not pulse like clocks. Planets do not broadcast radio signals at exact intervals. The team spent weeks testing alternatives. The signal held, perfectly regular, coming from a fixed point in the sky. They labeled it LGM-1. Little Green Men 1. The label was not entirely a joke. The team had genuinely run out of natural explanations. The possibility that something intelligent was transmitting a signal floated through their discussions, considered carefully and never fully dismissed until something better arrived. Then Bell found a second signal, same type, different location in the sky, then a third, an alien civilization building transmitters across multiple points in the galaxy was a stretch. Something natural was doing this. The explanation came from theoretical predictions made years earlier. In 1933, two astronomers named Walter Baade and Fritz Zwicky had proposed that collapsed stellar cores could form objects of extreme density, which they called neutron stars. In 1967, a theoretical paper described how such an object, if it rotated rapidly, might emit pulsed radio signals. Bell's signals matched that description exactly. The object she found was a neutron star rotating once every 1.337 seconds, its magnetic beam sweeping past Earth with each rotation. The discovery was announced in February 1968. It transformed neutron stars from a theoretical prediction into an observed reality. The Nobel Prize in Physics was awarded in 1974 for the discovery of pulsars. It went to Anthony Hewish and to radio astronomer Martin Ryle. Jocelyn Bell, who found the signal with her own hands, did not receive it. The decision drew criticism from scientists around the world. Bell herself responded with characteristic grace, saying she bore no bitterness. Many in the scientific community have never stopped arguing that the emission was wrong. The discovery opened a door into physics that has not closed since, and pulsars turned out to reveal something about gravity that even Einstein would have found stunning. Shine a flashlight in a straight line. The beam goes forward. It does not curve. It does not bend around corners. Light travels in straight lines. Einstein's general relativity predicted that gravity bends light, mass curves space, and light follows the curve. When light passes near a massive object, the path it travels curves slightly. This effect, called gravitational lensing, has been confirmed countless times. The gravity of galaxies bends light from objects behind them, creating distorted images visible from Earth. Near a neutron star, this effect becomes extreme. The mass packed into a 12-mile sphere curves space so sharply that light coming from the back of the star does not simply travel away into space. It curves around the edges. A telescope positioned at the right distance from a neutron star would detect not just the hemisphere of the star facing it, but also light from portions of the back surface, bending around the star's edge into view. You could see the back of the sphere from the front. This sounds impossible for any normal object, including stars, planets, and even white dwarfs. The curvature of space is too gentle for this effect to matter. A neutron star is the only known stable object in the universe, aside from things approaching black hole status, where self-lensing is a significant factor. Astronomers use this effect as a measurement tool. When a neutron star pulsates or has hotspots on its surface, the X-ray brightness should vary as those hotspots rotate into and out of view. On a normal sphere, a hotspot on the far side would be completely hidden. On a neutron star, the hotspot curves into partial visibility even as it rotates away. This changes the expected brightness pattern in a measurable way. By comparing observed brightness patterns with theoretical models, scientists can calculate the compactness of the star, the ratio of its mass to its radius. That ratio is one of the most important numbers for understanding what kind of matter fills the interior. In 2020, a team using a space-based X-ray telescope released measurements of a pulsar hotspot. By modeling the light-bending effect precisely, they constrained the star's radius to about 8 miles, a measurement accurate enough to begin distinguishing between competing models of the interior composition. The same light-bending effect also means the star looks slightly larger than it actually is. When you observe the surface of a neutron star from far away, you are seeing a wider angle of the surface than you would for an ordinary sphere. The gravitational lensing makes the apparent size of the star bigger than the real geometric size. This difference between apparent and real size is calculable from general relativity, and it gives astronomers another tool. Comparing the apparent size measured by telescopes with the expected real size from mass measurements helps constrain the structure of the interior. Light wraps around the star. Space curves so steeply that geometry itself breaks the rules of everyday intuition. And for any object that actually falls towards the surface, the journey produces something far stranger than bent light. A marshmallow weighs about 7 grams. Soft squishy, built entirely for toasting over a campfire. Drop one from a height of 2 inches, and it lands with a gentle tap, barely making a sound. Drop the same marshmallow from 1 inch above the surface of a neutron star. In the last inch of its fall, the marshmallow accelerates under a gravitational pull 200 billion times stronger than Earth's. By the time it contacts the surface, it is moving at roughly half the speed of light. The kinetic energy it carries at that velocity is equivalent to a nuclear weapon detonating on impact. A marshmallow, 7 grams. The force of an atomic bomb, this calculation is not an exaggeration. The physics behind it is straightforward. Kinetic energy depends on 2 things, mass and velocity. The mass of the marshmallow is tiny, but the velocity reached in even the shortest fall under neutron star gravity is enormous. The energy scales with the square of the velocity, so moving at half the speed of light produces kinetic energy far beyond anything the mass alone would suggest. The same math applies to everything that falls onto a neutron star, Gas drifting in from a companion star accumulates on the surface and compresses under the gravity. The hydrogen in that infalling gas gets heated to temperatures of hundreds of millions of degrees by the compression alone. At those temperatures, nuclear fusion ignites. The entire accumulated layer burns in a thermonuclear flash that astronomers observe as an X-ray burst. These X-ray bursts happen on neutron stars in binary systems regularly, sometimes multiple times per day. Each burst lasts a few seconds to a few minutes and releases energy equivalent to 10 to 100 times what our Sun produces in an entire year. In seconds, the gravity that produces this also means nothing on the surface stays raised for long. The impact of infalling material, even at microscopic scales, releases energy that heats and reshapes the crust. The surface is in a constant state of bombardment and resettling. Astronomers use X-ray bursts as measurement tools. The duration and brightness of the burst depends on the gravity, the temperature, and the composition of the accreted layer. By modeling those bursts precisely, researchers extract information about the size and mass of the neutron star beneath. In some binary systems, the accretion of material also transfers angular momentum, as discussed in the chapter on millisecond pulsars. The same infalling gas that causes X-ray bursts also gradually spins the neutron star faster. Over millions of years, a neutron star initially spinning a few times per second can be pushed to several hundred rotations per second purely by the angular momentum carried by the accreted gas. The surface of a neutron star is the most energetic real estate in the universe that still has a surface. Every particle landing there releases more energy than any chemical or nuclear reaction in a laboratory. The entire environment is defined by kinetic energy transformed instantly into radiation. That environment is lethal in ways that go beyond heat and impact. The geometry of the gravitational field does something specific to extended objects, anything larger than a single particle. It tears them apart before they can land. And the way it tears them apart is one of the most viscerally strange things in all of neutron star physics. Stand with your feet flat on the ground. Gravity pulls every part of your body downward. Your feet, your knees, your shoulders, your head, all pulled in the same direction with roughly the same force. The difference in gravity between your feet and your head, 6 feet apart, is so small it is completely undetectable without precision instruments. Now approach a neutron star. Gravity from a neutron star falls off with distance, as all gravity does. But because the gravity is so intense, and the star is so small, the fall-off rate is extreme. The difference in gravitational pull between 2 points, even a few feet apart, becomes enormous as you get close. Your feet, slightly closer to the star than your head, get pulled dramatically harder. The difference is measurable, then noticeable, then overwhelming. This difference in gravity across an extended object is called tidal force. The same effect is why the moon's gravity raises ocean tides on Earth. The side of Earth facing the moon feels a slightly stronger gravitational pull than the far side. That tiny difference stretches the oceans into an oval shape. Near a neutron star, the tidal force does not stretch oceans, it stretches atoms. A human body approaching a neutron star would first feel the tidal force pulling feet toward the star, faster than the rest of the body. Within moments, the differential grows past the point any biological structure can resist. The body stretches lengthwise, pulled into a longer and thinner shape by the gradient. Simultaneously, gravity from the sides compresses toward the center, squeezing the body narrower as it stretches taller. Physicists call this process spaghettification. The same word that describes the nuclear pasta shapes also describes what tidal gravity does to matter. The person, the machine, the spacecraft, whatever the object is, gets pulled into a long, thin stream. Eventually, the stream breaks into individual particles, each one following its own trajectory into the star. This happens far from the surface, long before reaching a zone where temperature or magnetic fields dominate. The tidal force reaches lethal levels. For a human body, The tidal disruption point lies roughly at a few hundred miles from the surface. Black holes do the same thing, and it has been observed. Astronomers have watched stars approach supermassive black holes and get torn apart by tidal forces, the stellar material stretching into a stream that spirals into the black hole. These events, called tidal disruption events, produce bright flares detectable across billions of light years. Neutron stars can produce similar events on a smaller scale. When a neutron star in a binary system pulls material from a companion, the material gets tidally stretched before it can accumulate on the surface. The stretching shapes the infall pattern and influences the X-ray burst behavior. The tidal force is not a special weapon of extreme physics. It is an ordinary consequence of gravity combined with size. Every gravitational object has tidal forces. A neutron star simply takes that ordinary consequence to an extreme, where nothing larger than a subatomic particle survives the approach. Objects fall in as particles, they land with explosive force, and occasionally two entire neutron stars fall toward each other. When that happens, the result manufactures something you carry with you every day. Every gold ring, every gold coin, every gold circuit on every computer chip on Earth came from an event more violent than any supernova. For decades, scientists debated where the heaviest elements in the universe come from. Elements like gold, platinum, and uranium require conditions far beyond what a normal star can produce. Ordinary stellar fusion builds up elements through iron. To create heavier elements, you need a process that can force neutrons into atomic nuclei at extreme rates. You need what physicists call a rapid neutron capture process, or R process. The conditions required are extraordinary: a flood of free neutrons, temperatures in the hundreds of millions of degrees, and densities comparable to a neutron star. For years, the leading candidates for where this happens were either supernova explosions or neutron star collisions. In 2017, the question was answered definitively. On August 17, 2017, gravitational wave detectors in the United States and Europe picked up a signal unlike any detected before. Two neutron stars, each roughly 12 miles wide, had been orbiting each other for hundreds of millions of years, spiraling slowly inward as they lost energy to gravitational wave emission. They had finally merged. The gravitational wave signal lasted about 100 seconds. Within 2 seconds of the merger, telescopes around the world detected a burst of gamma rays from the same location. Over the following days, telescopes in X-ray, optical, infrared, and radio wavelengths all tracked the aftermath of the collision. What they observed was a kilonova, an explosion powered not by nuclear fusion like a supernova, but by the radioactive decay of freshly synthesized heavy elements. The collision had thrown a cloud of material into space, and that material was rich in newly created atoms. The spectral analysis of the kilonova confirmed the presence of strontium, a moderately heavy element, within days of the merger. Later analysis found evidence for heavier elements consistent with gold and platinum production. Scientists estimate the collision produced roughly 3 to 5 times the mass of Earth in gold alone, and a similar amount in platinum and other heavy elements. Every piece of gold on Earth traces its origin to events like this, collisions that happened before our solar system formed, seeding the gas cloud that eventually became the Sun and its planets with the heavy elements produced in those mergers. The collision also confirmed something about neutron stars directly. The gravitational wave signal carried information about the tidal deformability of the two stars, how much each one distorted the other's shape as they spiraled together. That deformability depends on the stiffness of the matter inside. A stiffer interior would resist tidal deformation more. From the signal shape, scientists extracted constraints on the neutron star radius, narrowing the range of possible interior compositions. A collision 200 million years in the making, lasting 100 seconds, answering a question that had occupied astrophysicists for decades, and creating the gold in your pocket. And the ripples from that collision, the gravitational waves, traveled across 130 million light-years of space to reach detectors on Earth. Those detectors, and what they reveal about the deep interior, pushed neutron star physics into a new era. In Louisiana and Washington state, two enormous machines lie in wait. Each one consists of two tunnels, 4 kilometers long, arranged in an L shape. Inside each tunnel, a laser beam bounces between mirrors with extraordinary precision. The mirrors are isolated from vibration so carefully that the machinery can detect a change in distance smaller than 1,000th the width of a proton. These are the LIGO detectors, the Laser Interferometer Gravitational Wave Observatory. Their job is to detect ripples in space-time, waves predicted by Einstein in 1916, and first detected by LIGO in 2015 from two merging black holes. When two neutron stars spiral together and collide, the merger radiates gravitational waves. Space-time itself stretches and compresses as the waves pass. The distance between the LIGO mirrors changes by a fraction of the diameter of a proton. The machine detects it. The 2017 neutron star merger detection was a turning point in astronomy for reasons beyond just confirming the kilonova. For the first time, scientists observed the same event simultaneously in gravitational waves and electromagnetic radiation, everything from gamma rays to radio waves. This approach is called multi-messenger astronomy. Each type of signal carried different information. The gravitational waves revealed the masses and tidal deformability of the two neutron stars. The gamma-ray burst timing confirmed that light and gravitational waves travel at the same speed to extraordinary precision, a key test of general relativity. The kilonova revealed the heavy element synthesis. The radio waves arriving months later as the debris cloud expanded mapped the geometry of the explosion. Combining all those datasets gave scientists the most detailed picture of a neutron star merger ever assembled. Since then, LIGO and its European partner detector Virgo have accumulated additional candidate events from neutron star mergers. Each one adds data to the growing picture of neutron star interior structure. A separate project, the pulsar timing array mentioned in an earlier chapter, detected a gravitational wave background in 2023. That background, a rumble of gravitational waves coming from all directions, carries information about populations of massive objects merging throughout cosmic history. Analyzing it requires precise pulsar timing data from dozens of pulsars monitored over 15 to 20 years. Scientists are now building a next generation of gravitational wave detectors, significantly more sensitive than the current ones. The Einstein telescope, planned for construction in Europe, would detect neutron star mergers across a much larger volume of the universe. With hundreds or thousands of merger detections rather than a handful, the statistics would become powerful enough to measure neutron star properties with precision that current data cannot reach. Gravitational waves are a new sense for astronomy. They allow scientists to hear events that cannot be seen and to measure properties of matter that no telescope can access directly. For neutron stars specifically, the waves carry fingerprints of the interior encoded in the shape and timing of the signals. The interior those fingerprints describe gets stranger as you go deeper. All of the layers discussed so far, the crust, the pasta, the superfluid, the superconducting protons, these are relatively understood. The inner core is a different matter entirely. Every layer described so far has a reference point in laboratory physics. The crust density matches materials scientists have studied. The neutron drip line has an analog in nuclear experiments. The superfluid and superconductor behavior match phenomena observed in low-temperature laboratory conditions. Even the nuclear pasta, never directly observed, has a theoretical foundation in well-tested nuclear physics. The inner core has no laboratory analog. At the very center of a neutron star, the pressure reaches 5 to 10 times the density of a standard atomic nucleus. A nucleus is already the densest thing in ordinary matter. At 5 to 10 times that density, the particles are so close together that the distance between them is essentially zero. In any other context, particle physics tells us what happens when matter gets compressed. Atoms compress into nuclei. Nuclei can be forced closer together, up to a point. Beyond that point, the strong nuclear force switches from attractive to repulsive. The protons and neutrons inside nuclei repel each other violently at distances below a certain threshold, preventing further compression. Inside the inner core of a neutron star, the pressure has blown past that threshold. The matter is denser than the repulsive regime of the nuclear force should allow, yet the star does not explode. Something else is happening. What that something is, nobody knows with certainty. Scientists have proposed multiple possibilities, and the equations do not yet distinguish between them. The density is so extreme that it might change the identity of the particles themselves. Neutrons are composed of quarks, 3 per neutron. At normal densities, quarks are locked inside their host particles and cannot move freely. At 5 to 10 times nuclear density, the quarks might not stay locked. The pressure could be enough to dissolve the boundaries between neutrons entirely, freeing the quarks to move around as independent particles in a quark soup. This state of matter is called quark-gluon plasma. It existed briefly in the very early universe, fractions of a second after the Big Bang, before the universe cooled enough for quarks to recombine into protons and neutrons. Scientists have created it fleetingly in particle accelerators by smashing heavy atomic nuclei together at near light speed. If the inner core of a neutron star contains quark-gluon plasma, the implications are significant. The star's maximum mass, its radius, its cooling rate, and its response to gravitational waves all change depending on what the core is made of. A quark core is softer than a pure neutron core, meaning it compresses more easily, which would make the star smaller and more compact for a given mass. Current gravitational wave data from neutron star mergers has already begun ruling out the softest possible core models. The tidal deformability measured in the 2017 event suggests the neutron star matter is fairly stiff at the densities probed during the inspiral, but the very center, the deepest interior, remains beyond the resolution of current measurements. The inner core is the most extreme environment in the universe with a surface. Everything that happens there exists just one step from a black hole, and within it, scientists have identified not one, but 3 separate theories about the nature of matter that push physics to its theoretical limits. Every proton and neutron in the universe is built from 2 types of quarks, up quarks and down quarks, 3 quarks per particle. Those 2 flavors of quark make up essentially all the stable matter in the observable universe. Every atom in your body, every molecule in the ocean, every planet and star. Physics recognizes 6 types of quarks in total. The other 4, called strange, charm, bottom, and top, are unstable under normal conditions. Create one in a particle accelerator, and it decays in a fraction of a microsecond. Under everyday circumstances, strange quarks simply do not stick around. The inner core of a neutron star may not have everyday circumstances. At densities 5 to 10 times that of a nuclear nucleus, the energy state of the matter changes so dramatically that strange quarks might become stable. When that happens, neutrons can transform into heavier particles called hyperons. A hyperon is similar to a neutron, but one of its up or down quarks has converted into a strange quark. The most common predicted hyperon in this environment is called a lambda particle, a neutron-like object with one strange quark substituted in. Hyperons were first produced in particle accelerators in the 1950s and have been studied extensively. They are real, well-documented particles. The question is whether the conditions in the deepest neutron star core make them stable and abundant, rather than fleeting and rare. If the inner core contains hyperons, the pressure-density relationship of the matter changes. Hyperons are heavier than neutrons and interact differently with the surrounding particles. Their presence would make the core softer, meaning it would compress more easily under the same gravity. A softer core produces a smaller, less massive neutron star, for a given central pressure. This creates what nuclear physicists call the hyperon puzzle. Observations have confirmed neutron stars with masses around twice the mass of the Sun. If hyperons appear in the core and soften it as predicted, the maximum possible neutron star mass should drop to roughly 1.5 solar masses. The math says hyperons should exist. The observations say massive neutron stars exist. Both cannot be true using simple models. Solving this requires additional physics. Some researchers propose that hyperons interact with each other through forces not yet fully characterized, and those interactions provide extra pressure that stiffens the core enough to support the observed masses. Others suggest the hyperon phase is confined to a narrow density range and does not dominate the center. Still others argue the puzzle is evidence that something beyond hyperons, perhaps a full quark phase, takes over before the hyperon concentration grows large enough to cause problems. The hyperon puzzle has motivated some of the most sophisticated nuclear physics calculations of the past 2 decades. Teams have worked to measure hyperon interactions in particle accelerator experiments, specifically to feed better numbers into neutron star models. Each new mass measurement of a neutron star tightens the constraints. When a pulsar in a binary system has its mass measured precisely using orbital dynamics, that single number rules out entire categories of interior composition models. The most massive confirmed neutron stars, sitting around 2 solar masses, are among the most powerful data points in all of nuclear physics. Strange quarks hiding in the core of a city-sized ball, 12 miles wide, billions of light years away. The evidence for or against them sits encoded in how fast those pulsars spin, how much they weigh, and how they ring when 2 of them crash together. Everything is made of something smaller. Atoms are made of protons, neutrons, and electrons. Protons and neutrons are made of quarks. Quarks are bound together by particles called gluons, which carry the strong nuclear force. In every atom in the visible universe, quarks sit locked inside protons and neutrons. They have never been observed floating freely in nature, except in one place, the very early universe, fractions of a second after the Big Bang. At that moment, the universe was so hot and dense that quarks and gluons existed as a free-flowing soup. They had not yet combined into protons and neutrons. As the universe cooled, the quarks locked together, and matter as we know it formed. That primordial soup, the quark-gluon plasma, has not existed naturally anywhere in the universe since the first microsecond of its existence. Some physicists believe it exists right now, inside neutron star cores. At 5 to 10 times neutrons together may be enough to dissolve the boundaries between them. The quarks inside individual neutrons are held together by gluons. At extreme densities, when neutrons are packed so close that their internal quarks are nearly touching their neighbors, the gluons holding one neutron's quarks together become indistinguishable from the gluons in the next neutron. The boundary between particles blurs. The quarks stop belonging to individual neutrons and start moving as a collective. The result is a quark-gluon plasma similar to the one that filled the early universe, but maintained by pressure rather than temperature. Scientists have created quark-gluon plasma in laboratories by colliding gold and lead nuclei at nearly the speed of light inside particle accelerators. The collisions generate temperatures trillions of degrees hot enough to melt protons apart for a fraction of a second. The plasma created this way lasts about 10 to the power of -23 seconds before cooling and recombining. Inside a neutron star core, if it exists, the plasma would be permanent, sustained indefinitely by gravity rather than temperature. A quark-gluon plasma core would affect the neutron star's observable properties. The stiffness of the matter inside, its resistance to compression, determines the star's radius for a given mass. A quark plasma is generally expected to be softer than nuclear matter at the same density, meaning a star with a quark core would be slightly more compact than one with a pure neutron core. Some theoretical models include a phase transition at the boundary between the neutron region and the quark region, a sharp boundary where the nature of matter changes suddenly rather than gradually. If that boundary exists, it might ring like a bell during a neutron-star merger, adding a characteristic signal to the gravitational waves produced. Future detectors sensitive enough to resolve that signal could potentially confirm or rule out a quark core. Current detectors are close to the sensitivity needed, but have not yet resolved that feature clearly. The next generation of gravitational wave observatories planned for the coming decades may finally answer the question: the building blocks of all matter floating free inside a 12-mile ball. And there is a third possibility for the inner core, one that is in some ways the strangest of all, where matter stops being made of separate particles entirely. Two particles cannot occupy the same quantum state at the same time. That rule, the Pauli exclusion principle mentioned in Chapter 10, governs electrons, protons, neutrons, and quarks. These particles are called fermions. The rule applies universally to fermions, and it is the reason matter has structure. Without it, electrons would collapse into the nucleus. Atoms would not exist. And neither would you. Bosons play by different rules. Bosons are particles with a different type of quantum behavior. Photons are bosons. So are some composite particles made of fermions that pair up in a specific way. When bosons cool to near absolute zero or reach extreme densities, something remarkable happens. They stop behaving as individual particles. Every boson falls into the exact same quantum state simultaneously. The entire collection becomes one single quantum object, described by one wave function, acting in complete unison. This state is called a Bose-Einstein condensate. It was predicted by Albert Einstein and Indian physicist Satyendra Nath Bose in 1924. Scientists created it in a laboratory in 1995, cooling atoms to just billionths of a degree above absolute zero. They received the Nobel Prize in Physics in 2001 for the achievement. The condensate they created contained a few thousand atoms and lasted for a fraction of a second before warming. Inside a neutron star core, under extreme density, neutrons might form pairs. Two neutrons, bound together by the nuclear force at close range, act as a composite boson, rather than two fermions. When enough of these pairs form, they could collectively enter a Bose-Einstein condensate state, all sharing the same quantum state, all acting as one. The condensate would have no viscosity, behaving like the superfluid described in Chapter 14, but at an even deeper level. The entire condensate would respond to disturbances as a single quantum entity. A wave passing through it would travel as a coherent quantum wave, with properties distinct from any ordinary fluid. If this condensate exists in the core, its behavior under pressure and rotation would leave signatures in the star's observable properties. The speed at which the condensate responds to changes in the star's rotation could influence pulsar glitch behavior. The way it conducts heat might affect the star's cooling rate in a detectable way. Laboratory Bose-Einstein condensates have been studied extensively, and their behavior is well understood. The challenge is extending that understanding to a neutron pair condensate at densities and temperatures nowhere near achievable in any experiment. The theoretical framework exists, the experimental confirmation does not. All three inner core possibilities, hyperons, quark-gluon plasma, and Bose-Einstein condensate, are grounded in real physics. All three have experimental analogues in laboratory settings. All three are consistent with what is currently known about neutron star masses and radii. All three give different predictions for measurements that future telescopes and detectors will be precise enough to make. The inner core holds the answer. Getting to it requires tools that push the limits of what human technology can build. And even with those tools, the challenge is not just building the instrument. The challenge is that the object we are studying refuses to give up its secrets easily. 12 miles wide, heavier than the Sun. And after decades of study, the question of what lives in the very center remains genuinely open. This is not a gap in effort. Thousands of papers have been published on neutron star interiors. Dozens of space missions have been designed partly to answer this question. Some of the most powerful computers on Earth have run simulations of dense nuclear matter. The world's most precise radio telescopes have spent years timing pulsars to extract gravitational information. The problem is that the inner core sits behind layers of physics that each introduce their own uncertainty. Measuring a neutron star from the outside gives information about the average properties of the entire object. Extracting what the center alone is doing requires peeling away the contributions of every outer layer, and each of those layers has its own unknown properties. The equation of state is the key quantity. An equation of state describes how pressure and density relate inside a material. For water, for steel, for any material on Earth, this equation has been measured directly in experiments. For neutron star matter at core densities, it cannot be measured directly. The pressures required to recreate those conditions in a laboratory exceed the capability of any machine ever built. So scientists use indirect methods. Every observable property of a neutron star, its mass, its radius, its tidal deformability during a merger, its cooling rate over time, its pulsar glitch behavior, encodes information about the equation of state. By comparing observations with theoretical predictions from different equation of state models, researchers narrow down the possibilities. The problem is that the observations are hard. Measuring the radius of a neutron star from Earth requires separating the star's emitted X-rays from background sources, modeling how the magnetic field and surface temperature distribution affect the emission, and applying corrections for gravitational lensing. Each step adds uncertainty. Mass measurements are more precise. Pulsars in binary systems allow extremely accurate mass determination from orbital dynamics. The discovery of two solar mass neutron stars ruled out softer equation of state models, including many that included hyperons. But ruling out the softest models still leaves a wide range of possibilities. The 2017 gravitational wave detection constrained the tidal deformability, and hence the radius of the stars involved. Those constraints pointed toward radii of roughly 8 to 9 miles, which favors moderately stiff equations of state. But the uncertainty bands are still wide enough to accommodate both purely nuclear matter cores and quark matter cores. Scientists are currently operating a telescope on the International Space Station called NICER, specifically designed to measure neutron star radii by timing the X-ray pulses from hotspots as they rotate. NICER has released radius measurements for several pulsars with uncertainties of a mile or less. Each new measurement narrows the range. The next generation of gravitational wave detectors, the Einstein telescope and a planned detector called Cosmic Explorer, will detect neutron star mergers at rates hundreds of times higher than current instruments. Statistical analysis of hundreds of merger events will constrain the equation of state far more precisely than any single measurement can. The answer is within reach, possibly within a decade, possibly longer. The core of a neutron star has kept its secret for as long as humanity has been aware it exists. And what that secret reveals will not just explain neutron stars, it will tell us something fundamental about matter itself. Take Earth. All of it. Every continent, every ocean basin, every mountain range. The entire mantle stretching 2,000 miles deep, molten rock slowly churning over millions of years. The liquid iron outer core generating the magnetic field, the solid iron inner core sitting at the center under pressure so intense it keeps iron solid despite temperatures near 10,000 degrees. 6 sextillion tons of planet, spanning 8,000 miles from one side to the other. Compress it to neutron star density. The marble you are left with measures about half an inch across. Half an inch. You could roll it between your fingers. It would weigh exactly as much as the current Earth. Every gram of mass still present, crushed into a volume smaller than a pea. That marble, sitting on a table, would warp the floor through the table and straight into the Earth's core. Its gravity would be comparable to the current Earth's. The atoms of the table would not simply compress, they would dissolve into subatomic particles under the weight. The comparison works as a visceral demonstration of what density really means. Mass is mass. It does not change when you compress it. What changes is the volume it occupies. Neutron star matter reduces volume so drastically that the ratio between normal matter and neutron star matter is comparable to the ratio between a marble and a planet. Every cubic mile of a neutron star contains roughly the same mass as 3,000 full Earths stacked together, 1 cubic mile. Earth has about 250 billion cubic miles of volume. A neutron star has a total volume of roughly a few hundred cubic miles. This compression ratio also explains why neutron stars are among the most powerful gravitational lenses in the universe, outside of black holes. Concentrating Earth-equivalent mass into a marble-sized space does not change how much gravity exists. It changes where that gravity is concentrated. The field becomes asymmetric at small distances in ways that bend light dramatically. The marble thought experiment also has implications for how neutron stars affect their surroundings at large distances. A neutron star's gravity at a distance of 1 million miles is identical to a normal star of the same mass at the same distance. Gravity depends on mass and distance, not on how spread out the mass is. Far away, a neutron star and an ordinary star of the same mass are gravitationally indistinguishable. It is only up close, within a few hundred miles, that the extreme concentration of mass produces the spectacular effects described throughout this journey. The bent light, the tidal stretching, the extreme escape velocity, all of these arise because the mass is concentrated into an impossibly small volume. The marble comparison is a useful anchor. The most extreme physics in the universe operates inside something you could fit in your pocket. And inside that marble-sized volume, the physics extends further into strangeness than any of the solid layers above. Sound itself, the vibration of matter, reaches speeds in the inner core that science is still working to understand. Sound is a pressure wave. Something vibrates, compresses the surrounding material, and that compression travels outward. In air, sound moves at about 760 miles per hour. In water, faster, about 3,400 miles per hour. In steel, faster still, about 11,500 miles per hour. The pattern is clear. Denser, stiffer material carries sound faster. The inner core of a neutron star is the stiffest, densest material in the observable universe outside a black hole. The speed of sound in any material has a theoretical upper limit. According to relativity, nothing with mass can travel at or above the speed of light, about 670 million miles per hour. For a long time, physicists assumed the speed of sound in any material topped out well below that limit. The theoretical cap for sound in an ideal ultra-dense fluid was thought to be about 35% of the speed of light. Recent theoretical work has challenged that assumption. Research published in the past few years examined what the equations of dense nuclear matter actually predict for sound speed in the inner core. The results found that the speed of sound in neutron star core matter likely rises significantly above the 35% threshold at the densities present in the center. Some models put the sound speed close to 60% of the speed of light in the densest regions. Sound traveling at 60% the speed of light, 200 million miles per hour, through matter compressed into a space smaller than a city. This matters because the speed of sound in a material is directly connected to its stiffness. A stiffer material, one that resists compression more forcefully, carries sound faster. The high sound speed predicted in the inner core implies the material there is extremely stiff at those densities, stiffer than pure neutron matter models predicted. This stiffness observation comes from analyzing neutron star masses and gravitational wave data together. The fact that neutron stars can reach two solar masses without collapsing into black holes requires a stiff interior. The stiffness needed to support that mass corresponds to a sound speed well above the old theoretical limit. The precise sound speed profile through the star, how fast sound travels at each depth, encodes the equation of state as surely as mass and radius measurements do. Scientists are working to extract that profile from combinations of gravitational wave, X-ray, and radio pulsar data. If the sound speed in the inner core truly approaches 60% of the speed of light, it changes theoretical models of the core composition. A pure quark-gluon plasma at those densities was thought to be relatively soft. A material with this sound speed behaves more stiffly. Either the quark matter is interacting in unexpected ways, or the inner core contains something else entirely, a new phase of matter that physics has not fully characterized. The measurement of sound speed in matter 10,000 light-years away, inside an object 12 miles across, using nothing but light curves and gravitational waves, is one of the great triumphs of modern astrophysics. And everything this journey through the neutron star has revealed comes together in a final truth about what these objects mean for everything we think we understand. You have traveled through 12 miles of the most extreme matter in the universe, through an iron shell harder than any diamond, past a boundary where atoms fall apart, through pasta-shaped structures, stronger than any material ever built, into a superfluid ocean spinning without friction, down through a superconducting layer generating magnetic fields 1 trillion times stronger than Earth's, and finally to a core where the very nature of matter is uncertain. Every layer pushed physics harder than the one above it. Every layer revealed something that could not be predicted by studying matter under ordinary conditions. The neutron star is not just an exotic object. It is a laboratory that runs experiments no human facility can replicate. On Earth, the most powerful particle accelerators can briefly create temperatures and densities that mimic conditions from the first microsecond after the Big Bang. Those experiments have produced extraordinary discoveries, confirming the standard model of particle physics and revealing quarks, gluons, and the Higgs boson. They last for fractions of a second and require billions of dollars of equipment. A neutron star runs a more extreme version of those conditions continuously, across a volume of hundreds of cubic miles, for billions of years. The physics operating inside the core touches every fundamental force. Gravity, running at its maximum non-black hole intensity, shapes the large-scale structure. The strong nuclear force, which holds all matter together, operates at densities where its behavior has never been measured. Quantum mechanics, the set of rules governing particles at small scales, determines whether matter is superfluid or superconducting, or something stranger. And relativity, the theory describing how mass warps space and time, governs the behavior of light, sound, and clocks near the surface. All four fundamental frameworks of physics operate simultaneously inside one object, 12 miles wide. When two neutron stars collide and the gravitational waves from that collision reach Earth, those waves are carrying equations. Encoded in the shape and timing of the signal is information about how matter behaves at densities 5 to 10 times beyond anything reproducible in a laboratory. Extracting that information is the work of the next generation of detectors and the physicists building them. The answers will not just explain neutron stars, they will constrain the equation of state of dense matter. That equation of state tells us the fundamental relationship between pressure, density, and energy at extreme conditions. It feeds directly into models of how heavy elements form. It tests whether our current theories of the strong nuclear force are complete, or whether new physics is hiding in the most extreme environments. There is also a question of limits. Neutron stars exist at the boundary of what matter can be without becoming a black hole. Understanding them tells us where that boundary is and why it exists. It tells us what the universe allows and what it forbids. A spinning iron ball, 12 miles wide, heavier than the sun, glowing at 1 million degrees, sweeping a magnetic beam across the galaxy hundreds of times every second, hiding in its core a state of matter that has existed nowhere else in the universe, since the first microsecond after the Big Bang. It is there right now, spinning, cooling imperceptibly slowly, keeping its secrets just a little longer, waiting for the instruments that are finally powerful enough to ask the right questions.